Everybody, it's video notes 11.2, acids and bases, and it's all about pH today. So here's three more specific objectives that you can use, and hopefully you'll know when you're done. Also, please keep using chapter 16 as a reference and practice. So to know if your solution is acid or base, you need to know its pH, you need to know whether it's a strong or weak, you need to know whether it's an acid or base, and you need to know its concentration. So water is actually in equilibrium with itself. What? So you could have H2O liquid plus H2O liquid, and they run into each other. Boom, 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 collision theory. And sometimes when they do that, an H3O plus and an OH minus forms as a hydronium or hydrogen ion is transferred from one water to the other. Okay? Because of that, we could also write it as H2O liquid in equilibrium with H plus and hydroxide. Okay, so we can write an equilibrium constant expression. It's called a KW. So we do products over reactants. So the products are H3O plus and OH minus over, oh look, they're liquid, so we don't have to write it. This is always going to be a constant of 1.0 times 10 to the negative 14. So that means in water, this and this are equal. So the H plus concentration in water is 1 times 10 to the negative 7th. And the OH minus concentration in water is 1 times 10 to the negative 7th because they're equal to each other. So that's why water is neutral. Now if we take the negative log of H plus, we get negative log of 1 times 10 to the negative 7th, and we get pH 7. What? Nice. Okay. So the pH seesaw, the higher the concentration of hydrogen ions, the lower the pH. So H plus, if there's a lot of H plus, then the pH is around here. Okay. As that evens out, you get your seesaw, you got H plus and OH minus are equal, then you're right about here. Okay. And vice versa. So as one goes out, the other goes down to keep the KW at 1 times 10 to the negative 14th in water. Okay, so here's three formulas that if you memorize these and use them correctly, you'll be able to get some pH. Woohoo! Okay, so where's the H plus and the OH minus come from? Well, one is a strong acid or strong base. They completely dissociate. So strong acids, their concentration tells you they're H plus. So what is the pH of 0.00356 molar HCl solution? Well, we've got HCl, and we're going to get total H plus and Cl minus. So if this was initially 0.00356 molar, I mean, none of that, that's going to change. All of this will dissolve, so we'll get 0.00356 molar of that and 0.00356 molar of that. So that was plus x, but we know it's all of it. So our change in our equilibrium are the same. So H plus equals 0.00356. So what's the pH of the solution? pH equals negative log of 0.00356. And we get the H plus of, pH of 2.45. Okay, so 1, this is an acid. Make sure you know that it's an acid and that it's a strong acid. Strong acid. So it completely, all of this turns into hydrogen ion. Okay, what about for base? Well, base is 100% ionization, but instead of making H plus, it makes OH minus 100%. Okay, so what is the pH of 2.45 times 10 negative third molar NaOH? NaOH will completely dissolve into Na plus OH minus. Okay, so initially, if we have 2.45 times 10 to the negative third molar of that, none of that, that's going to change to get to equilibrium minus all of it. So we're going to get X and X. But at equilibrium, that X is 2.45 times 10 to the negative third and 2.45 times 10 to the negative third. But be careful. This time, It's the concentration of OH minus. OH minus is 2.45 times 10 to the negative 4. So now we have this equation, Kw, because these are all water solutions, is equal to H plus times OH minus, which is always a constant of 1 times 10 to the negative 14. So because this is hydroxide, we have to plug it in there. So we find out that the H plus concentration is 1.0 times 10 to the negative 14 divided by 2.45 times 10 to the negative third. So the H plus concentration is 4.08 times 10 to the negative 12. So pH equals negative log of 4.08 times 10 to the negative 12, which is 11.39, which makes sense because this is a base, so its pH will be over 7, and it's a strong base, so it's making a lot of hydroxide, so there's its pH. Okay, now, that's for strong. You just take the concentration and you use it, or you find H plus from a base and then you use that. If you have a weak acid or base, it's at equilibrium. So you have 0.42 molar HC2, so 1, it's an acid. 2, it's weak, right? So that means not all of this breaks apart, okay? So we have to know an equilibrium constant. So I'm going to show you this table, and this is a table of Kas. Right? If you notice, these are strong, right? So their Ka is very large. But then the rest of these are weak acids, and you can see that their Kas are small, which means there's more reactants than products when you do an equilibrium expression, okay? And so here's the Ka for acetic acid. So here's the equation. You should be able to write this. HC2H3O2 is aqueous, okay, because those are surrounded by water molecules. You have H plus is aqueous, and then you have C2H3O2 negative, which are also aqueous. And a Ka for this is going to be the products, H plus concentration times acetate ion concentration. And then we do have to put this on the bottom because it's aqueous, HC2H3O2. And the reason this is aqueous is because some of the water surrounds these, surrounds those, and surrounds those, and you have some of everything at equilibrium. Okay. So if we start out initially 0.42 molar of this, we have none of that, none of that. That's going to change because some of that's going to dissolve. Dissociate, if you will, dissociate. So at equilibrium, 0.42 minus x is going to give us x of that and x of that. Okay, why? What is x going to be? X is going to be small because the ratio of products over reactants equals 1.8 times 10 to the negative fifth, so that means it's mostly the bottom number at equilibrium. So you can plug in x for hydrogen ion, x for acetate ion, and 0.42 minus x for the concentration of the acetic acid. Okay, now we solve this. Solve. Right? And we'll find out that we get x squared plus 1.8 times 10 to the negative fifth x minus 7.56 times 10 to the negative sixth. Okay, so now we can use quadratic solver. We have A, we have B, and we have C. And so then we plug it in, and we find out that x equals 0.00274. What does that mean? That's this, right? So, which is H plus. So then that equals H plus. Are we done yet? No, because we need to get pH. So pH is going to be equal to the negative log of, and I'm going to change it to scientific notation. That's 10 to the negative third. So pH is going to be 2.56 for this solution. Okay. Why do we have to do all that work? Because acetic acid is a weak acid, so we have to do the equilibrium because we're going to have some of everything at equilibrium. When we do strong acids or bases, we only get H plus or OH minus, all of it. Okay, so you'll get a Ka table. You don't have to put it in your notes, but if you want some examples, you can. Ka greater than 1, strong acid. Ka less than 1, weak acid, because it's always products over reactants, and if this is essentially 0, then that's going to be a big number. Remember, it's products over reactants. And then if there's not a lot of products, if this is a small number and that's a big number, then you'll get more of the reactants when it's at equilibrium. Okay. Same with bases, but with bases it's called a KB, right? Because it's but it's still products over reactants. And for KB, it's KB greater than 1. It'll be a strong base. We'll get this table too. KB less than 1 is a weak base. Right, so you have to know what equilibrium is, a ratio of products over reactants. All right, calculate the pH of 0.35 molar N2H4. Step 1, base. This is a base. Step 2, strong or weak? Weak. All right, base and weak. So we need to write a dissolving equation. So we'll do N2H4. So this is where your knowledge of Bronsted-Lowry stuff comes in. It's going to be liquid. This is aqueous. This is a base in equilibrium. So it's going to, N2H5 is going to gain an H and a plus. Okay. And then water is going to lose an H and a plus. Okay. So the KB is going to be the products. N2H5 positive times your other product over the reactants, but this is a liquid, so N2H4. Okay. Now, you can look it up on the chart here. This is hydrazine, 1.7 times 10 to the negative 6. 1.7 times 10 to the negative 6. So, initially, we have 0.35 molar of this. None of that, none of that. That's going to change. Some of that's going to dissociate, and we'll get some of that and some of that. So at equilibrium, we'll have 0.35 minus x for that, and we'll have x of that and x of that. So that we could plug it in. X and x over 0.35 minus x. So here we go. Again, solving the quadratic formula. We're going to get an x squared plus 0.35 plus 1.7 times 10 to the negative 6x minus 5.95 times 10 to the negative 7. So we plug in our A, our B, and our C into quadratic solver, quadratic formula, and we find out that x equals 0.000007705. Right? What is x though? X is hydroxide. Right? Equals OH minus. So we got to do that extra step if we want pH. We got to use the KW equation. And we got to say so that's 1 times 10 to the negative 14. And we say that H plus times the OH minus equals this. We know the OH minus, so H plus is going to be equal to 1 times 10 to the negative 14th divided by 0.0007705. And we find out that H plus is, oh man, I didn't do it on my practice, so I'll do it right now. We've got 1 to the negative 14 divided by 0.12307705, and we get 1.298 times 10 to the negative 11. Right, So what's pH? Well, do over here. pH equals negative log of 1.298 times 10 to the negative 11 equals, and we're going to put that in. Okay, so negative log, I'm plugging in my calculator, 1.298, negative log, I did it wrong, but I got to do it again. Negative log of 1.298 to the negative 11th exponent, and I get pH equals 10.88, 10.89. Right, so do 2 decimal places on your pH. So I plugged it in. So we find out this is basic, which it should be. All right. So there we go. That's how you get pH of a weak base. So just remember that bases give you OH minus, acids give you H plus. So the X is H plus for an acid, the X is OH minus for a base, and then you gotta figure it out. Okay. So you gotta know your calculator and your math equations. pH is actually used in real life to diagnose problems. You could have problems in your swimming pool, blood poisoning, soil, antacids and acid rain, all of this pH helps us with. Okay, and like you read about, why do sinkholes form? Why are the coral reefs dying? Okay, how is your food digested? Okay, what is acid rain? All of the stuff you read about. So you should be able to do, thanks, Matilda, some stuff in the book, and make sure you can do this stuff. You know, you should memorize this equation, memorize the pH equation, pH equals negative log of H plus concentration, right? And then as this goes up, it's acid, so that's going down. If that goes up, it's base, so that goes down. But if it's water, they're equal. Okay. All right. Keep on keeping on. Oh, look, there's your self-determined objectives. All right.